normal shock waves, and we have used relation for normal shock. So what is different or what is interesting in oblique shock, that we'll see. We'll also talk about expansion waves in this chapter also. So this is the syllabus, but some portions we have already covered for this unit, and now we can start with the oblique shock and related topics. So this slide you already have seen. So what is the difference is, normal shock, the flow is perpendicular to the shock. Okay, there is no component which is parallel to the shock wave. But in oblique shock, the shock is at an angle to the flow. So once you see in later slides that once we basically when we are studying oblique shock, what we can do is we can divide this incoming flow in two components. One will be in perpendicular direction to the shock like this. Let me draw it for you. So this is a vector, right? So I can say that we have two components. One is going in this direction and one is going in this direction. Can I do that? Yes or no? Basically, it is just the vector direction. This is your resultant vector, and I'm breaking x and y components, and I will analyze accordingly. That we'll see as we move. So that is the basic difference between a normal and oblique shock. Another interesting fact is that when you have a normal shock, behind the shock, the flow becomes subsonic. After the shock, once you pass through the shock, the flow becomes subsonic. While in oblique shock, the flow could be supersonic even after passing through the shock. That is something different or interesting about oblique shock, and why that happens, we'll see in later slides. Okay, now let us look at some examples. So these are the slides that I have shown you previously. So this shock is what, normal or oblique? Oblique. So flow is coming like this. Flow is coming, let us say, in the parallel to the x-axis, in the x direction. So shock is at an angle to the flow. Then it is called oblique shock. And we also have discussed about this slide earlier. Now you are clear that this is an oblique shock. Flow is at an angle to the shock. So we'll in this chapter we'll cover this oblique shock. We'll also talk a bit about expansion fan, and we'll wind up this. So this is also one of the given topics. If anyone is interested, you can try these three combinations and you'll get some interesting results. So if anyone is remaining now, those who have not got any topic, I will recommend you can take this one, because it will also help you in class. Once you get this result, it will be interesting to share with everyone, and we can also probe some quantities. We can look at pressure distribution or velocity distribution. So that will be really interesting. Okay, moving on. So what happens is that when so this is about any obstacle, right? Other than that, if the flow is, let us say the passage is turning like this, or there is a step or a corner. So when supersonic flow, basically your m1 is more than 1, it turns into itself. Itself means that like this, the path is getting narrower, let us say. Then we see oblique shocks are generated. Okay. Now when it is turned away from itself, like this, then expansion fan is formed. So this is what we are talking about in the last chapter. So when I say that the shock tube inside surface should be smooth, if suppose you have a small perturbation like this, it could be very small, but it will definitely generate a shock wave. That is what we try to avoid for a shock tube. Okay. So this is the general schematic, how we represent oblique shock and expansion fan. Fine. So this is called a compression corner. Basically, this is a corner where you generate the shock. There are actually a lot of interesting studies on how this shock leg basically interact with the boundary layer. This is a very active area of research. Many PhDs are getting generated here. How this, in this very small region, how this shock reacts with the boundary layer. And this is called expansion corner. So around this corner, you see a fan is generated. Okay, so let us look at some points on oblique shock. So flow is deflected into itself, what we saw in the last slide. Then oblique shock is formed at the compression corner to become parallel to the solid wall downstream of the corner. So once it deflects, then it follows, tries to follows a path which is parallel to this. That is what is mentioned in words here. And all the streamlines are deflected to the same angle, theta. Okay, we'll see there are different angles related to shock, theta and beta, and we'll also see a plot of that. But let us say this is theta is the angle of shock, resulting in uniform parallel flow downstream of the shock. So this is the downstream where we see uniform parallel flow. That is the understanding or assumption. Theta is called flow deflection angle. By what angle your flow is getting deflected, right? And across the shock wave, Mach number will definitely decrease, pressure will also decrease, and density will also decrease, and temperature will increase. And the corner which does the flows itself is called compression or concave corner. Okay. Now let us talk about expansion fan. So it is a convex corner and flow is turned away from itself. Okay, this is what I was talking about. I should have put this picture here, but anyway. So streamlines are deflected to the same angle. Basically, they are expanding in that direction. Okay, resulting in uniform parallel flow. Let me keep that here so that will be easier to discuss. Let us keep that picture here so that don't have to go back and forth this slide. Right? Okay. So let us talk about expansion fan. So all the streamlines are deflected from the same angle. So whatever the flow is coming, it gets deflected, and basically we are assuming a parallel flow. So I'm not drawing it very nicely, but let me try it again. Basically, the idea is that the streamline remains parallel. Okay, whatever angle they turn through the fan, that is something we'll look into, but at the end, all these lines are parallel. They are moving parallel to basically this wall. Sorry. The last. Okay, so they are moving parallel to this wall, that's all. Now, Mach number is increasing, M2 is more than M1. That is something which is, this is exactly opposite of what you will see in a shock wave, right? Pressure, density and temperature decrease. Flow turns suddenly across the shock and turning is gradual across the expansion fan, and hence all flow properties through this expansion fan change smoothly. Okay. So you see that there is no, in a shock, the streamlines will, let me go to the shock. You see the streamline will turn suddenly. You can see that here it is like a corner, it will smoothly move from here to here. That is one major difference between a fan and a shock. Okay, there will be a step change in properties, there will be a gradual change in properties. Except for this, at the corner, there is near the wall, it is a step change, otherwise, it is all a gradual change. Okay, this is the exception. near the wall streamer. That's the point. Other than that, it is all smooth and gradual change. Now, this both of these features they are in 2D and 3D flow. Okay, normal shock generally we consider that this is one dimensional, but for basically for most of the practical example that we'll consider, we'll see that the shock is actually oblique. There are very few examples that we have seen where normal shock is there, but this is a more simpler and easier to understand concept. So we start with that and then we gradually move on to more practical or more frequently observed oblique shocks. Okay, so let us see how we can break up this shock. Basically break up the component of velocities. So let us say this is oblique shock lying at some angle beta to the incoming flow v1, and this velocity it gets tilted, and the resultant velocity after the shock is v2. So let us say it deviates from its path by an angle theta. Is this fine? Shock is at an angle beta and the fluid vector of the incoming velocity is changing at an angle theta. Is this clear to everyone? Yes or no? Anyone please respond? Yes. Fine. Please keep talking. I will not know whether I have lost connection and I am talking to myself. So it is important that you say yes or no. Fine. So let us first break it down. So let us say this is the V1, I will break it down into Vx1 and Vy. Okay, these are the two components, simple vector addition, that's all. Now once it passes through the shock, I can say that this is a normal shock, and let us say I have flow is coming at Vx1, so it acts like a normal shock. Okay, and Vx1 it will change to Vx2. Okay, this will be changed. Now what about Vy? Will Vy change or will it be the same? So what I have done here is basically I have just taken this picture and let us say I just rotated it a little bit. Because of that rotation, what you see inclined, that has become like this. This is the same shock which you see in this picture. Once you rotate, this is now horizontal, now it becomes, this is that V1. Let me give some color to it. So this is the original picture where you see shock is, flow is coming to oblique shock. Now this is the V1. I've just rotated it to show some things clearly. So this flow is coming and hitting it. Now I assume that once I divide into these components, x and y components, I say that x component is coming and it behaves like a normal shock. It passes through it and there is some change based on normal shock relation. That's all. Now what about Vy? What will happen to Vy? Will it decrease or increase or remain same? What will happen? Anyone? So, correct. So Vy will not change because it is parallel to the shock. The changes that will happen, that will be normal to the shock, parallel to the shock, it will not have any effect. So because of that, Vy will be the same. If Vy is, let us say, high, then the resultant V2 can also be supersonic. So this is one tricky condition which is not there in normal shock. Okay, now let us see what can we do. So V1 and V1 is basically Vx and vector addition of x1 and y. This is what is shown here, and this beta will be, let us say this is beta. You take the tan of beta, you will get Vx1 by Vy. So tan inverse of this is beta, which is also called as shock angle. So this is the angle between the shock and the velocity vector, resultant velocity vector of the incoming flow. That is called beta. And this flow is turning, right? Flow is turning by this angle theta. This is more clear actually. So flow is coming and turning by an angle theta. That theta is called flow deflection angle. I think this diagram has some problem. It should, this is the right version. So this theta is basically flow deflection angle. How much the flow has deflected from its original path, right? And the Vx1 is more than Vx2, Vy is same. So what happens is that you see this, this velocity component is changing, it is decreasing, and this is the same. So basically this resultant velocity after the shock, it will not go in the straight line, it will turn towards the shock. So we say that flow is turning towards the shock. You can see here this diagram. This diagram is more clear. Let me make it clear to you. So once you see that flow is coming toward the shock, there are two ways it could move. It could either, see, one is it goes straight. This is the original path. So now it could either move towards the shock or away from the shock, like this. Okay, but generally for oblique shock, what happens is that it moves toward the shock. Okay, so whenever you, let me draw it. So whenever you have a situation like this, or Lewis, let me draw it this way. So whenever your flow is like this and here is the shock, you will say that after the shock, it will turn towards the shock. Okay, it will be near to the shock, that's all. So this is how generally oblique shock or flow across an oblique shock behave like. Fine. So we need to look into some relations and effects, but we have time. So we'll stop this now.